You know, it's kind of wild when you think about it. That giant steam engine that basically kicked off the Industrial Revolution and the tiny cells inside your own body, they're both playing the exact same game. And this game has rules. Not just any rules. I'm talking about the fundamental laws of the entire universe, the ones that control energy, heat, and work. So let's crack open the rule book for this cosmic game, a little something called thermodynamics.
Okay, so what's the connection? What does a massive steam engine have in common with, just rubbing your hands together when it's cold? Well, turns out they are perfect examples of thermodynamics in action. One takes heat and turns it into useful work, moving a train down a track, and the other, it takes the work from that friction and turns it right back into heat to warm you up. Same principles, totally different scale.
And really, at its heart, that's what this is all about. Thermodynamics, it's the science that lays out the relationship between heat, energy, and work. It is, quite literally, the rulebook for how energy moves around and changes form. Okay, let's get a little more specific for a second. Thermodynamics is all about the big picture. It's what we call a macroscopic science. What that means is, it's not interested in tracking every single little molecule bouncing around. No way. It looks at the whole system, like all the gas in a container, and describes it with things we can actually measure. Stuff like pressure, volume, and temperature. All right, so if we're going to understand the rules of this energy game, we've got to meet the key players first. Everything else we're going to talk about is built on just three fundamental ideas: internal energy, heat, and work. Seriously, if you get these three, the rest of it just clicks into place.
First on the roster is internal energy. We usually just call it U. The easiest way to think about it is it's all that chaotic energy inside a system. It's the sum of all the jiggling, vibrating, and zipping around of all the molecules. It's the energy a system has just by being there. Okay, next up is heat, or delta Q. And listen up, because this is a really, really important distinction. Heat is not something a system has. It's energy that's being transferred. It's energy on the move, always flowing from something hotter to something colder. Think of it as a process, an action, not a thing you can own.
And our third and final player is work, delta W. This is the other way to transfer energy. But unlike heat, which is kind of chaotic, work is more organized. It's a coordinated energy transfer, usually something mechanical, like a gas pushing a piston up. And just like heat, it's a process, it's something that happens.
And this quote just nails it. Saying a gas has a certain amount of heat is just as weird as saying it has a certain amount of work. It makes no sense. It's like saying you have a run. You don't have a run, you do a run. It's an action. What the gas does have is its internal energy.
You know what? Here's the best analogy. Think of a system's internal energy as your bank account balance. It's a number. It's what you have right now. Now, heat and work, those are the deposits and withdrawals. They're the actions that change your balance. You see, you don't have a deposit, you make a deposit. Same idea. Okay, we know the players. Now it's time for the rules of the game. And we're going to start with the 0th law. Yeah, I know, weird name. It's because it was so basic, so fundamental, that they came up with it after they'd already named the first and second laws. And this law is the one that gives us the very idea of temperature. Let's just do a quick thought experiment here. Imagine you've got three things, let's call them A, B, and C. You take A, you touch it to C, and you just wait. Eventually, they get to the same temperature and heat stops flowing. They're in what we call thermal equilibrium. Now, you do the exact same thing with B and C. All right, they're in equilibrium too. So, here's the million-dollar question. What do you think happens when you touch A and B together?
The answer is absolutely nothing, not a thing. They're already at the same temperature, already in thermal equilibrium with each other. Now, I know that sounds super obvious, right? But that simple, obvious fact is actually incredibly important.
And that is what the 0th law is all about. It just formalizes that idea. It tells us that if two things are in equilibrium with a third thing, they must be in equilibrium with each other. It means there's some shared property there, and we call that property temperature. This is the whole reason a thermometer works. All right, moving on to the big one, the first law of thermodynamics. Now, if this whole thing is a game, the first law is rule number 1. You can't win. That's it. You can never, ever get more energy out of a system than you put into it.
So here's how it's stated a bit more formally. It's basically just a rule of accounting for energy. It says that any heat you add to a system has to go somewhere. It can't just vanish. Some of it goes into boosting the internal energy, making all those molecules jiggle around faster. And the rest? Well, the rest could be used to do work, like pushing a piston. And this gets us to one of the most fundamental rules in all of physics, the conservation of energy. You've probably heard it before. Energy cannot be created or destroyed. It can only be moved around or changed from one form to another. That's it. That's the law. And the famous equation for the first law is just like a perfect balance sheet. The heat you add, delta Q, has to equal the change in internal energy, delta U, plus the work done, delta W. Everything has to add up. Every single bit of energy is accounted for, with nothing left over and nothing mysteriously appearing. So, the first law says you can't win. Well, the second law comes along and says, you know what? You can't even break even. This is where things get really deep. This is the law that gives time its direction. It's the reason why some things happen and some things just don't.
I mean, think about it. According to the first law, there's nothing stopping your cold cup of coffee from spontaneously boiling. By sucking heat out of the air in your room, energy would be totally conserved. But have you ever seen that happen? Of course not. It's absurd. We know, instinctively, that heat flows from hot to cold, not the other way around. And the second law is what tells us why.
So one way to state this, called the Kelvin-Planck statement, basically says this: you cannot build a perfect engine. It is physically impossible to build a machine that's only job is to suck up heat from one place, say the ocean, and turn 100% of that heat into useful work. Can't be done.
What this really means is that there's always a tax, an energy tax. Anytime you try to turn heat into useful work, you're gonna lose some of that energy as waste heat. It's unavoidable. It's the reason your car engine gets blistering hot and needs a whole cooling system. You can't break even. Nature always takes its cut. Okay, so if a perfect 100% efficient engine is impossible, what's the next best thing? What's the absolute limit? To figure that out, we have to talk about something called the Carnot engine. Now, this isn't something you can go out and buy. It's a purely theoretical idea, a perfect idealized engine that sets the ultimate speed limit for efficiency in the universe. This perfect engine runs on a perfect four-step cycle. First, it pulls in heat from a hot source while staying at that hot temperature. Then it expands and cools down, but without letting any heat escape. Third, it dumps its waste heat into a cold place, staying at that cool temperature. And finally, it gets compressed back to where it started, all ready for the next cycle. It's a perfect loop. And here is the absolutely mind-blowing part of this whole idea. The maximum possible efficiency of any heat engine, I don't care if it's a steam engine or a nuclear power plant, depends on just one thing: the difference in temperature between the hot part and the cold part. That's it. The bigger the temperature gap, the more efficient you can be. But as you can see from this beautiful little formula, as long as that cold temperature is anything above absolute zero, you can never hit 100% efficiency. It's impossible.
And that kind of brings us to a final, really big thought. We often talk about the second law as the law of increasing entropy, which is just a fancy way of saying that things in the universe naturally go from a state of order to a state of disorder. Things fall apart. So, if that's an ironclad, unbreakable rule for the entire universe, this relentless march from order to chaos, what does that mean for its ultimate fate? What's the end of the game? That's definitely something to chew on.